Hello and welcome to my tutorial on data structures. My name is Aubrey Orr and I will be going through this tutorial that I have made for you guys, and I will also be doing some code alongs. So the purpose of this tutorial is to teach you about some of the most fundamental data structures that we use. And as a result, you should be able to learn what a queue is, how to add to and remove from queues, what a linked list is, how to traverse and manipulate data from a linked list, what it means to be a doubly linked list, what a binary tree is and how to traverse it, why they're helpful for programming efficiency, and how to add to and evaluate data in a binary tree. So again, this is assuming that you have some basic understanding of programming, you have some experience, you're not necessarily a beginner, but maybe you haven't gotten too deep into data structures. And if that's the case, then this tutorial is for you. So the course is set up into three different modules. We have one on queues, one on linked lists, and one on trees. And honestly, the difficulty kind of goes up with each one. So I would recommend just starting from the beginning, or just start wherever you need. If maybe you already have queues down, so you can switch wherever you want. So click on this link, and this will take us to queues. So queue, what is a queue? Well, a queue is a type of data structure that utilizes, you can see this acronym I have here, first in, first out is what that stands for. And so you've heard the word queue before, and you've been in queues before. And so with queues, what happens is, as you can see that I have illustrated here, let's say your data structure is set up for this line. Queues happen so that the first person into the line or the first item gets used first before the other items. And once it's used, it's the first one to leave. So in our queue here, you see how 0 is the front. If we were to delete something from this queue, we would work with 0 and then delete it. So you've probably been on a phone call before. Maybe it was even at BYU and you were calling about your scholarship and they said, oh, an associate will speak with you soon. Your approximate wait time is 8 minutes. That's because other people have called before you and they're closer in line to the queue, where you might be like 4, they're like number 1 or 2. But once they get used and they're deleted from the list, you get closer. And so obviously as programmers, it's a good skill to have is how to work with queues. And so there are a few things that I'm going to show you how to do. One is enqueue, that's when you add to a queue, and another is dequeue. So as you can see in my code example here, adding to a queue is fairly simple. You've probably done this before. In Python, when we do it, we add to the end. So the new value we want to add is here, in this case, is 10. So we wouldn't add to the front or to the middle, we would add it to the end, so that way we maintain that first in, first out approach. And to dequeue, it's the opposite. We need to utilize the current value. As you can see, I have my new value equals Q0, and Q0 is always the first item. It's kind of coincidence that they're both 0 in this case. I made these their index number just to be easier to understand, but essentially it will always be the first item. Then we're going to pop that first item once we're done working with it. All right, so now that we have those basics out of the way, I have an example problem. So imagine you have been hired to work for BYU Idaho's customer service department, and it's your job to program their queue. You might solve the problem something like this. In the field, it is more likely to be working with additional files to read from, but this is outside the scope of this assignment, so we will stick with inputs. And so like I said, a lot of times you're not going to be using necessarily an input when you're working with a queue, but in this case, that's going to be our example. The purpose is learning how to get used to queues. So we're just going to ask the customer to either add to the queue, remove a customer, or press 2 to quit. So again, if choice equals 1, then enter the customer's name, and we just append it to the end of our customer queue. And then if it's choice number 2, we just pop the first item. Pretty easy to get the hang of. Now, here's the challenge problem. So let's say you're applying for an apartment complex, and this apartment complex has several different layout plans for its floor. You have a floor that is just one room, and also a floor that is 2 bedrooms. And you might have a preference, whether, let's say you want to live by yourself, you might go for the 1-room one. If you have a spouse and maybe some children, you might want to go for the 2-bedroom one. And if you really don't care, you just want to be on the list and get whatever you can get, then you can also have a preference of both. And so your job is to create a queue that uses the first in, first out approach, and also takes into account their specific desired apartment. So if I have an example down here, I can actually show you. So we're going to loop through it. And so let's say we were to type 2. Well, the first person to go wouldn't be Jesse because he specifically wants 1. Then we move on to Herbert. He wants both. So Herbert would be able to go. So Herbert has been removed from the list. And then if we were to do 1, Jesse would go. And then 0 would obviously quit it, and so on and so forth. So yeah, try working on this. And if you want, you can pause the video right now and see if you can figure it out yourself. Go ahead and copy this into your IDE. This queue here, which is a queue that holds several dictionaries or maps. While you're doing that, I am going to do the exact same thing. So now that I have that copied in there, and we have our queue, let's just get started. So this is now at the front. We have our apartment queue, and since we're going to be doing a while loop, an often approach that I like to do with while loops is just have a variable called keep on, and then that's going to equal true. And then I just say while keep on. And this way I can just set it to false once I want to end my while loop. And it really doesn't matter if this is inside or outside the while. So let's first ask the user for the next available apartment. So we're getting data, and that data is going to be, oh, an apartment just opened up. What is it? So we'll say available apartment equals, and then we'll just do an input. And type 0 to finish, and that way they have a way out of the loop. So if you go down, well, let's first address that. So if available apartment equals 0, and we don't need to set this to an integer because we're not going to be doing math with it or anything. We're just checking to see what it is. So if it equals 0, keep on, set that to false, and we will also break. That's good. All right. So now that gets that out of the way. If you want to get out of the system and then press 0, that should do it. So we should now set a variable for currently held. Because remember, we're going to be going through this list, and when we're going through a queue, oftentimes we do want to manipulate the data with the current one that we're on, which is always the first. So currently helped, we're just going to initialize this to none. And then let's also set an index, which equals to 0. And we're just going to use this as we move through our list for deleting it. So like I said, oftentimes you're going to delete, like the index will always be 0 because you just delete the first item. But we have a special case here where sometimes it's both and sometimes it's not necessarily the first one. So let's say if somebody asked for 2, we wouldn't just delete the first one. So set the index to 0. Next step, we're going to want to have a for loop. We'll do for pair in apartment queue, and this is just going to loop through each dictionary here. And then let's do if pair, and then we have, oh, you can see right here, type. Pair type, we'll do equals, we'll do available apartment. Or we should have another case, pair, then Oh, I spelled pair wrong again. Pair type equals, and we should also include both because that way it really doesn't matter. Then we want our currently helped person to be that one that we're on in that moment. So we'll just do currently helped equals pair, and we'll do name. Perfect. All right, so now that we have that, we are almost done. We have the currently helped pair equals pair name. Let's go ahead and pop this now. So we can do apartment q dot pop, and this is our DQ. So that way they will get out of the list, and we'll do index. And again, we're going to also keep counting this through with each loop. So index. Now let's go ahead and print the data. So I'm just making these empty prints to kind of for formatting, honestly. And now we have this F string currently helped has been removed from the list. And if this were an actual part, we have some kind of system set up where they also enter their phone number and their email, and then we would send them an email, congratulations, send them like the listing contract or whatever it might be. But we don't have that information. So we're just working with the queue for now. So they have been removed from the list. And let's go ahead and add just another print. And we'll go ahead and break because we only want to do just one at a time. We don't want to do every person who has one or every person who has two or every person that has both. So let's go ahead and do, and now that we're outside of this if, let's plus equal that index. One. Oh my goodness. There we go. And let's test this. All right, and we can just do what they have. I think they have their example. First was 2. Yep, Herbert has been removed from the list. Let's do 1. Oh, I'm silly. Here. All right, so that's a user error. I entered the number 2, not the actual thing. Okay, so, all right, restarting. Please enter the apartment type. All right, so let's type it out 2. There we go. Herbert has been removed from the list. That's good. Okay, now let's type 1. And Jesse has been removed from the list, which is exactly what we wanted because it skipped Jesse, went to Herbert for both, and then went to, and then once we did 1, then it did Jesse. So let's see if our exit loop works, and it does. I am just going to add colon equals just to make it look better there. So that's how we do and program queues. And so we're going to now move on to the next part. So let's go to back to here. All right, so the solution is there. I included the file. And so let's go back to the home. All right, so queues, we got that down. Now to move on to linked lists. And linked lists, just like trees, as you're going to see, they can be a little bit overwhelming at first, but don't worry, you're going to get the hang of it. So what is a linked list? We've been working with lists so far that worked essentially in a way as you just keep counting one thing to the next, and they're in a specific order, and they're next to each other in memory. Linked lists are not necessarily next to each other in memory, and they don't necessarily increment the same way that that static or dynamic arrays do. A linked list is characterized by each item points to the next item. So as you can see in my diagram here, item A one of its attributes, often this will be in a class, so a.next will be B, and b.next will be C, c.next will be D. And we're going to be working with doubly linked lists. Oh, also, the first item is always the head, last item is always the tail. If there's only one item, it's both the head and the tail at the same time. All right, so then the next item, or essentially what we're going to be working with, is called a doubly linked list. And doubly linked lists not only have a next feature, they also have a previous feature. Now with heads, the previous feature is going to be none. The tails, the next feature is going to be none. But everything in between is all going to have a next and a previous feature. So, and this is the one that we're going to be working with. This is easier for us to traverse. So inserting. How do we insert into a linked list? This is very important because when you're dealing with a linked list, you're not just worried about the one item, but you're also worried about its neighboring items. And it's really important to get this order down, because if you mess it up, it will mess up your entire list and you won't be able to iterate through. So first, to insert into the head, we just check if there's none. If there is none, like I said, the head and the tail are the same, and they're going to be the new node. Otherwise, so if there is a head, we need to replace that head with a new one. So the new node dot next, try to envision this in your mind. The next of the new node is the current head. So that way the head is now the second item. The head's previous is now new node. And now we set the head to the new node. So again, we're not only worried about our item itself, we're also worried about our head and its attributes. So our head's previous attribute is now our new node. Very similar for tails, except for this time we're going to be doing stuff like previous instead of next. So again, if none, set it to the new node, both the head and the tail, and then new node dot previous equals self dot tail. So imagine we're at the end here, but we want to insert a tail here. Now the previous of our new node is D. And now self.tail.next equals new node. The next of our tail is now our new node. And then we just set the tail attribute to our new node. And all is well. There's a little bit more included when we insert into the middle, and you're going to insert in the middle, obviously, as you're incrementing it through, and you want to insert after a certain point or whatever it might be. But we set the new node, and again, it's confusing, but if you just think about, you're not only worried about the node itself, but its neighbors as well. So we have our new node, which is the node, and then if we want to insert it where the current is, the previous of our new node is current. Our new node's next is the current's next. So if we were to insert here between B and C, our previous would be B, and then B's next now becomes our new next because we're in between them. We get sandwiched. And then current.next.previous, so the current one that we're on, its next one, its attribute of its previous is now our new node. Again, we have to worry about our neighbors. So this is current, this is next, its previous is now our new node that would be in the middle somewhere. And then current.next equals new node. And so we just set the next of our current to the new node. Again, very important to follow these steps. If you don't, you're going to have some problems with your linked lists. Now, removing is oftentimes easier. If the head and the tail are the same thing, that means there's only one item, and just set them both to none. Otherwise, all you have to do is set, if we're removing the head, set the head's next previous to none. So the next thing previous, it doesn't have a previous, and then the self.head equals self.head.next. So if we wanted to get rid of A, set B's previous to none, and then set this to the head. And very similar again with a tail. I recommend just like going through this, writing this code in your own IDE, but this is the code on how to do it. And removing from the current is a lot simpler than inserting into the current. We just set the current next previous to the current previous, and the current previous next to the current next. So that kind of just overlaps. This one's next is now, let's say if we were to have something here, this one's next is no longer this thing, it's this thing. This one's previous is no longer this thing, it's this thing. And I explained these in the paragraphs too. So just read over those if you're having a hard time. All right, now traversing. So the traversal list, let's talk about traversing going forward. You want to start somewhere, start at the head, have a while loop, and while the current is not none. Remember, once we get to the end of the list, that's how we can tell we're at the end, because the node will be none. So then we will do whatever you want to do with the data. Here, we're just going to print it, is the example. And then you just keep on rolling. You set the current equals the current dot next. And so you just keep going until you're at the end. If we were to reverse the linked list, we would set the head to, rather than having the current be the head, we would have the current be the tail. And we would do current equals current dot previous. So where this really shines is it's similar in a lot of ways to a dynamic array, except for we do all this work to help us get better performance on the front end, inserting into the front, removing from the front, and it has an 0.1 performance with that, which is a lot better than some arrays. Once you start getting into some massive data structures, that can come in handy. And so you might be remembering from our queues, oh wait, we always take from the front. And so bingo, queues and linked lists work very well together. So just keep that in mind. Now time for our challenge problem. All right, so let's say you have to remove all items in a linked list with a specific value. And how would we do that? Well, we would create our linked list class and with a subclass of node underneath it. And then let's go ahead and we set, again, the next, each node has a next and the previous. And we've already seen how we insert into our head and insert into the tail. So now the remove function, removing from the head, basically to achieve this goal, we want to separate our functions into a remove head, a remove tail, and then when we remove the value, if we find the head, we're going to call that function. If we find that our current value is the tail, we're going to call the remove tail function. And anything else, we can just implement what we saw earlier on how to remove from the middle, which is right here, which is you can achieve on just these two lines. And so copy this code into your IDD. If you get stuck, this is essentially how you do it. So if we just have this if statement, if current.data equals value, then current, then we're just going to remove the head. And if the current equals the tail, we're going to remove the tail. And if it's in the middle, we're going to remove it. Pretty easy. And again, just traversing. So I really think you can do that. For sake of time, I'm not going to walk through everything for this one, but I do want to help you guys with the second problem because it's a little bit trickier. So I'm just going to read this. Now time to spice it up a little bit. Edit the program so it still removes each instance of the value, but also that after the loop, it displays how many instances of the value were found. For example, if we were to do linked list.remove 5, the function should output 1 instance of 5 removed because we only have one thing right there. We just have the 5. And if we were to do 2, it should print 3 instances of the 2 value, which we have right here. So let's go ahead and do that. So do much. Says we can keep this the same, except for just adding, should be adding somewhere. Again, we want to count each instance of a value and display that as well. So let me go to the solution. And I am going to walk through this with you guys. So let's say we have, this looks right. We have our insert, head, remove. Okay, good. All right. So now that moving up to here, I have this remove head. Again, this is pretty, this is not that bad. Removing from the head, we just do self.head. So we check to see if the tail and the head are the same thing. So tail. Then self and self.tail. All right, not too bad there. And then elif self head is not none. Head dot next, like we showed earlier, dot previous. I know sometimes it feels like a lot of work, but you have to remember to do these steps, equals none. So the head's next, previous is now none. Good. Self dot head equals self dot head equals self dot head dot next. And that is what we want. And then very similar thing now for the tail. So we're going to do, honestly, I'm just going to copy this because I think we get the idea of that now at this point. And equals, yep, okay. Let's do an elif. And we'll do self, basically the same thing, but now opposite. Tail is not none. And I'm going to do self.tail dot previous dot next equals none. Self and self.tail equals self.tail dot previous. All right, now time to move on to our remove function. So not only do we want to remove each value, but remember we want to also print off each instance of that value. So we're going to, pretty similar to the example we had, we're going to set a current, because anytime we want to traverse a list, we have to do that, and oftentimes start at the head or the tail. So our current equals the head. And let's set, kind of similar how we did to the queues, a number of instances outside of our while loop. And we will just count that each time we find one. So if current is not none, so this will keep going to the end. And now let's check if current dot data, yeah, current dot data equals value. So now if the value is the same, so we're moving through our linked list, and now if the value is the same, now let's check to see our multiple options. We can check if current equals self.head. Now, thankfully, since we made those functions, it's as easy as just removing or calling those functions. So remove head. Now we'll do an elif. Current equals tail. And we're going to do self.remove tail. And now we can do an else because it's not the head or the tail, but it's something in the list, and that means it's anything in between. And again, we just do those two lines that I showed earlier. So next on prev equals current previous, essentially just overlapping it so it doesn't exist anymore. And then current prev next. And that should work. Now we have to implement the part of our function. that keeps track of each occurrence. So after all these ifs, part of our original was if it was the same data, so we know that it is, so we're just going to add that here. Number of instances plus equals 1. Great. And then press enter again. And then outside of the if, but still in the while, let's add something for us to keep going through the list. So current equals current dot next. Great. And now let's go ahead and break out of this while. So once we're out of the while, remember we need to display how many instances of the value there were. So just for formatting, I'm going to make 2 different ones. I'm going to do number of instances. And I'm just going to say equals 1. So if there's only 1 found, just for grammar, I'm just going to do its own separate thing, which is going to say 1 instance of the value, and then if that's anything else, print string, and we're going to do we'll do instances of value. And this should work. Let's make sure that I called it down here. Remove 5. Okay, great. Let's go ahead and run this. We might get an error, but we'll see. Awesome. Looks like it worked. So we print off our list, and then right here we print off, then we remove it, and then 1 instance of the value 5. And then we print off our list, 5 is gone. 3 instances of the value 2, when we do it there, and we print off a list and it's gone. All right, so that solves that challenge problem. Let's go ahead and move on to the next one. So we're go to the home page. And guys, we're 2/3 done. We are almost done with this. Now we just need to move on to trees. Fun. All right, so trees, like linked list, the more you practice it, the more you get used to it. Linked lists and trees are similar, but we categorize trees in that they're a data structure that have roots and branches. So a data structure of a tree starts with, it's also characterized by parents and children. So items can have multiple children, but they can only have 1 parent in trees. We're going to be working with binary trees, which, as the name suggests, each parent can only have a maximum of 2 children. However, they can have 0 children or 1 child and still be considered a binary tree or part of a binary tree. It's just most important that they do not go over 2. So here is, we're going with binary trees. The way that this is useful is we can set it up in something called a binary search tree. And binary search trees will help us achieve possibly O of log n efficiency, which is very important, which is very good as well. So for us to make a binary search tree and for us to insert into it, I have these 2 functions here, so that way we can start at the root and then insert it, because you're going to need to use recursion. Before I go into that, I want to look at this diagram here as we look at how to insert in, kind of at the same time. So the first item is always the root. So you start at the root, and this is a binary sorted tree. And so you see how each item only has maximum of 2 children, but some don't have any, and some only have, I guess none in this example will have only 1. But they could have 1 if they wanted to, but some, they either have 2 or none. So this is a binary search tree. You have parents, and then you have children and siblings. And then the very last ones are called leaf nodes, and each of these little dudes are subtrees. So the way that we sort it is each item can only be in the tree once. So if we find that the data equals the same data, we won't do anything with it. We just leave it where it is. And then, but things go on the left if they are less than our current value, and they go on the right if they are greater than our current value. So as you can see, when this was made, 56 was inserted into the tree, then 30 was, and 30 is less than, so it goes on the left. 70 is greater than, so it goes on the right. Then let's say 60 was inserted. 60 is greater than 56, goes in, oh, but it's less than 70, so it's going to go right there. And then if 22 is inserted, it's less than 56, and it's also less than 30, and so that goes there, and so on and so forth. So you're probably starting to see why we're going to need to use recursion for this. So we check to see if it's less than the value, we go to the left, and if there's nothing there, we insert it. If there is something there, we do it all over again and we use recursion. Eventually, we will find a spot where there is empty room for us. After we're done doing that, then we do the same thing, but on the right. So a balanced binary search tree is important for us achieving O of log n. Otherwise, if it's unbalanced, it essentially has the same performance as a linked list. So how do we tell if something is a balanced binary search tree? Well, it's characterized by no subtree on either side is significantly greater than the other side. So if we were to insert this differently, and 3 was inserted first, then 11, then 16, then 22, it would kind of just go in a straight line, which is not best. It's not what we want. And there are algorithms that we can use to solve this. If you're interested, it's a little outside the scope of those algorithms, but the AVL algorithm is something you can research. Otherwise, for our purposes, we're just going to be inserting it into a way that it maintains order. So not 3, then 11, then 16, then 22. We will do something like how they have here. So to traverse a tree, again, I have these two functions for the purpose of checking if there's nothing in there, but also to help us start at the root. And this is good, especially if your methods and their variables are private, so you can only access them within the class. Otherwise, you probably could get around this just by inserting the root in other ways, but I have these two functions for that purpose. So we start at the root, call the function. And so here, let me try and illustrate this for you. So you check and see if node is not null. So if there's an existing node, this is how you go through it. You start on the left side always, and this will help us get it in a good order. So you keep going to the left until there's nothing found. And you remember with each recursion, you have to print the current value. And then once you're done with that, then you go to the right. So let me try illustrating this. So if we were to implement this function, we would start here. We would go to the left. We remember that we need to print this, but first we need to go to the left. Then we remember we need to print this, but if there's something to the left, we're going to check and see if there is. If there is, we have to go there. And we keep going until we get to 3. Nothing to the left of 3 or the right of 3, so we print 3. Then we go back up, remembering that we have to print the current value. So then 11 will print, and then it will go down the right side. And then 16. Then it starts back up here, and 22 would print, nothing on the right side, so 30 would print, and then it goes to the right side. And we basically do this all the way down the tree. So now that we went through traversing, we talked about inserting into the list. Let's do the example problem. So imagine you've been tasked with getting the number of items in the list. So try to think about how you would achieve this. There's several ways, but there's actually a very easy way to achieve this example problem. And we can do that just by keeping track of the items as we're inserting into the list. So You can see here in my binary search tree, I not only have the root initialized, I also have the size initialized. When I insert into the root, if there's not an existing root and I add one, the size now equals 1. And now anytime we insert again, just plus equal 1 to the size. And that will very easily solve how to keep track of the size of your tree. And that way you can just call it, I have this print size, which just gets there are self.size items in this tree, and that works every time. You can copy this code if you want. Moving on to a slightly more difficult problem. So now it's your opportunity to try this yourself. I'll allow you to pause the video, but add a method that can get the sum of all items in your linked lists. So just copy this code above. You're going to keep a lot of it into your IDE. Then when you're done with that, copy these test cases at the bottom of it. And again, you are going to want to get the sum of all items. So here you can see this comment I have. Here you will call your function, name the function whatever you like. I would have included it in here, but I wanted you to figure this out in any way possible that you see fit. You can have whatever arguments you want or whatever you feel is the best way to solve this. So I'm going to give you a few seconds to pause the video, and then I'm going to go through it with you. All right, so now, hopefully you had a chance to try and solve that. I'm going to go through it with you as well. So let's go back here. And first things first, like it said, we are going to copy this in. That, and that looks like that copied all right. And let's also remember to copy these. It's right here. So we have that. I will put these at the bottom. All righty. So just to make sure everything is inserted, okay, let's go ahead and run this before we add our new function. And there are 7 items in this tree. Great. All right, so we want to make our new function that will get the sum of all items. So let's just name that. Also, there are 2 ways to do this. And the first way is equally as easy as getting the size. Essentially, all we would need to do is just do wrong function. We would, right underneath the size, self.sum equals 0. We would initialize that to 0. And then self.sum equals. And if we're inserting into the root, this is just going to equal data. And then every time we insert after it, we can just do sum plus equal our data. So it is honestly kind of a cheat doing this. But this is probably the easiest way. Self.sum plus equal data. But since we already did the easy way out last time, let's actually try and make a function. I would normally just keep track of it this way, but let's say you're in an interview and they ask you to specifically make a function to do this without having access to its initialized self. So let's go ahead and make that function. So let's just call this getSum. And then this will include self and a starting node. So let's do if node equals none. Let's just get this one out of the way because that's the easiest. We can just say, oh, there's nothing there, return 0. And this will also be our base case for recursion. So else, we're going to return our value plus all the value on the left side plus all the value on the right side, and to stop when there's no value on that side. So node value plus self dot get sum node dot left. So again, that's using recursion, but now we're starting with the left side. Plus self dot get sum. We're going to do node dot right. So we're adding those three, and that should work. So each time we're looping through, this is our base case, and we'll return the value every time. So if we come down here, let's call this function and see if we got it right. So we'll do print my tree dot get sum. And like I said, we're going to want to put in the root. That's going to be our first thing. Save it and let's run it and cross your fingers. Everything was entered right. And there it is, 99. And you can do the math on a calculator if you want, but that should equal 99. And that's how you solve the second challenge problem. All right, so that is it for this tutorial. Thank you everybody for joining me on this. I will post this to GitHub, and this has been a real pleasure going through and learning these data structures with you. Again, my name is Aubrey Orr, and I am submitting this to Canvas to be graded for my final assignment. Thank you for joining, and I hope you all have a wonderful day. Goodbye.